Okay, so we all use the internet, right? Every single day. But how many of us actually know how it works? I mean, really works. Well, forget those dense, complicated textbooks. Today, we're going to crack the code, and we're going to use a pretty unusual source as our guide.
So check this out. For decades, computer science students have had to face this exact final exam. And yeah, it's a test, but what if it's more than that? See, these aren't just random questions. They're basically the keys, the fundamental principles that make our entire digital world tick.
And that is our big idea for this explainer. We're going to treat these old exam papers like a secret blueprint, right? If we just answer the most common, the most critical questions that show up year after year, we can actually piece together how the whole thing is built. I'm talking from the actual wires buried in the ground all the way to the apps you use on your phone.
All right, so where do we even start? Well, you have to start with the most basic question of all. How are we all plugged in? I mean, before a single bit of data can go anywhere, there has to be a connection, right? Either a physical wire or a wireless signal. It's the first question on these exams, so it's the first place we're going to look.
The first big concept that pops up on these exams, like all the time, is something called network topology. Now that sounds super technical, but it's not. The easiest way to think about it is, it's just the map of a digital neighborhood. That's it. It's how all the computers and printers and servers are physically laid out and plugged into each other.
And just like real neighborhoods can be designed in all sorts of different ways, so can computer networks. For example, a star topology, that's kind of like a cul-de-sac where all the houses connect to a central roundabout. A bus topology is like one long main street that everyone's house is on. And a ring is, well, exactly what it sounds like, a big circular road. And these basic layouts are the building blocks for everything, from your tiny home network, that's your LAN or local area network, all the way up to the entire global internet itself, which is the ultimate WAN or wide area network.
Okay, so we've got the map, the layout, but how does the information actually travel along those paths? The exams have a fancy name for this, transmission media, but it really just boils down to two main types. First, you've got guided media. That's anything you can physically see and touch. Think about those giant fiber optic cables running under the ocean, or even just the Ethernet cable plugged into your computer. Then you've got unguided media. That's all the invisible stuff, like the Wi-Fi signals that are probably flying through the air around you right now.
All right, we're connected. But wait, just being physically linked up isn't enough. Not by a long shot. If two devices are going to talk to each other, even if they're right next to each other, they need a set of rules, a shared language. And this is where the exam blueprint starts to get into the nitty-gritty of how digital conversations actually happen.
In the official computer science models, this job belongs to something called the data link layer. Its whole purpose in life is to make sure data gets transferred reliably between two devices that are directly connected, what they call adjacent nodes. A great way to think of it is like a traffic cop managing just one single street, making sure every car, or in this case, every message, gets to its immediate neighbor perfectly, without turning into a garbled mess. Now, one of the biggest problems you run into at this local level is a thing called flow control. And trust me, this question is all over these exams. Just imagine you're trying to tell a story to a friend who writes really slowly. If you talk at your normal speed, you're just going to overwhelm them, right? They'll miss half of it. Well, the exact same thing happens with computers. A fast computer can totally flood a slower one. So how do you solve a problem like that?
The answer is actually really elegant. It's called the sliding window protocol. Here's how it works. The sender agrees to break up the information into little chunks, called packets. Then, it only sends a few packets at a time. That small batch is the window. After sending, it just waits. It waits for the receiver to send back a little message that says, "Yep, got him." As soon as that acknowledgement comes in, the window slides forward, and the sender knows it's okay to send the next batch. It's a simple but totally brilliant way to make sure the conversation always happens at a pace both sides can handle.
Okay, so talking to your immediate neighbor. Sorted. We've got that handled. But the internet isn't local. It's global. So how in the world does an email you send from your kitchen find its way to a server on the other side of the planet? Especially when there are millions, maybe billions, of possible paths it could take. Now that is the next big challenge we need to tackle.
The answer to that massive problem, and you'll find this in literally every single exam paper, is routing. Honestly, the best analogy for it is to think of routing as the internet's own built-in GPS system. It's the magic that happens behind the scenes, finding the absolute best path from your computer to, say, the Netflix servers, and all the way back again in a tiny fraction of a second.
But for that GPS system to work, it needs one crucial thing: addresses. Every single device that's connected to the internet,
Your phone, your laptop, your smart TV gets a unique address, and that is its IP address. It's just like a postal address for the real world. You can't send a letter without a street address and a zip code, and you can't send a packet of data without an IP address to tell it exactly where to go.
So how does routing actually work? Well, these exams show there are basically two main philosophies. The first is called distance vector routing. This is like trying to navigate a new city by asking a local for directions, but they only tell you how to get to the next street corner. You just know the very next step, and that's it. The other philosophy is link state routing. This is like having a complete, high-res satellite map of the entire city on your phone before you even leave your house. You can see the whole network and find the best path. As you can imagine, they both have their pros and cons, which is why it's such a classic exam question.
Okay, great. Our data now has an address and a GPS to find its way. We're getting somewhere. But think about it. Not all online conversations are the same, are they? Sending an email is a totally different experience from being on a live video call. So we need another set of rules, this time for the type of conversation we want to have.
And this brings us to a really core design principle of the internet, which is all about trade-offs. The big question is this: do you need your conversation to be 100% perfect and reliable, even if that makes it a little bit slower? Or do you need it to be lightning fast, even if that means a tiny piece of information might get lost along the way? There's no single right answer, and these exams are always forcing students to weigh that choice.
So the internet gives us two main tools for the job, and you guessed it, this comparison is on pretty much every exam. The first one is called TCP. Think of TCP as sending a package with certified mail. You establish a connection, you get delivery confirmation, you get a signature, and you know everything arrives safe and sound and in the right order. The other tool is UDP. UDP is like sending a postcard. You just scribble a message, drop it in the mailbox, and hope for the best. It's incredibly fast, but there's absolutely no guarantee it'll get there or that a whole stack of them will arrive in the order you sent them.
And this chart really breaks it down for us. You use the reliable one, TCP, for things that absolutely have to be perfect. Think about loading a web page or sending an email. You can't have letters or words missing, right? But you use the super fast one, UDP, for things where speed is way more important than perfect reliability. We're talking live video streaming or online gaming. I mean, who cares if a few pixels are missing for a split second in your video stream? That's way better than the whole thing grinding to a halt to buffer, right?
All right, we've made it to the top. This is the final layer. So we've got our physical connections, we've got our local rules for talking, we've got our global GPS, and we've got ways to manage the type of conversation. The final question is, what do we actually do with all this incredible infrastructure? And just as important, how do we keep it all safe? This brings us to the last major section in our exam blueprint. And this is where you see all those acronyms you probably recognize. These are the application protocols. HTTP is what lets us browse the World Wide Web. SMTP is the engine behind sending email. FTP is for transferring files. And then there's the unsung hero of the whole system, DNS. Think of DNS as the internet's phone book. Its only job is to translate the easy-to-remember names we type, like google.com, into the numerical IP addresses that computers actually need to work. But of course, with all this amazing activity comes risk, so it's no surprise that these exam blueprints always end with security. And the first line of defense is cryptography. It's a fancy word, but it's really just the ancient art of secret messages. It's all about scrambling your data with a secret key so that even if a bad guy intercepts it, it just looks like gibberish. They can't read it without that key. And rounding out our security tour, we have the firewall. The bouncer analogy is perfect for this one. A firewall is like a digital bouncer standing at the front door of your network. It inspects every single piece of data trying to come in or go out. If it sees something on its do not enter list or just anything that looks a little bit suspicious, nope, you're not getting in. It's one of your most important lines of defense.
And there you have it. That's the whole journey. Just by following the clues in these old computer science exams, we've basically walked through the entire structure of the internet. We started with the physical connections, right? Then we moved to the local rules of conversation. After that, we saw how the internet's global GPS, routing, helps us navigate the maze. Then we learned how to pick the right kind of conversation with TCP or UDP. And we finished up with the apps we use every day and the digital guards that keep us safe.
So now that you've seen the whole blueprint laid out, I want to leave you with one final question to think about. When you think about your own digital life, What part of this hidden architecture is the most essential to you? Is it the lightning-fast, anything-goes speed of UDP that powers all your entertainment and gaming? Is it the rock-solid, no-mistakes-allowed reliability of TCP that you depend on for work and email? Or is it all the invisible stuff, the silent, constant work of the routers and firewalls that just make everything possible in the first place? The answer, I think, really reveals what the internet truly means to each of us.